Okay, so the topic we are talking about today is t-statistics, and we are basically following up our tour through the GLM. So basically, after looking at the estimate distributions, we are now looking at another statistic that can be formed based on the GLM theory, and which of course is fairly popular in terms of statistical testing, namely the t-statistic, and it's also fairly popular in terms of fMRI data analysis, because these images that you always see where you have the brain and then you have something lighting up, so something being yellow or reddish somewhere. What you see here, so these blobs that you see on the brains, they are color representation of T statistics. Usually, sometimes it's F statistics, but most of the time it's actually T statistics if it's these typical contrast condition A versus condition B. That's what's then visualized and what's also actually reported in tables then. So T values and their associated P values in some way, which goes beyond what we are going to do today. But it's actually, so in terms of fMRI data analysis, it's a very common thing to see T statistics. What I want to do first is do a little bit of a review of where we are with the GLM, because it's the new year and there was a break. Then introduce the t-statistic or t-statistics, and look at some examples, actually 3 examples, which are fairly quick. And then talk about the T distribution, and then discuss its use in hypothesis testing, where we don't do, at this point at least, a formal approach, but discuss the general idea of hypothesis testing based on the t-statistic, because I think it's so the whole thing works a little bit different maybe than you are used to. So I guess you talked about t-statistics, or everybody has seen t-statistics in undergraduate statistics for 1 sample or 2 sample t-test. And there it was all about, I think, rejecting or not rejecting the null hypothesis. And then there was this somewhat mystical procedure where you compute certain things, and then you look up in a table, you look up some p-value, and then you reject or not reject. And so I'm on purpose trying to give a different perspective of this approach here, also because this approach doesn't necessarily help you that much for fMRI data analysis, because you can't make the link between t-statistics and design matrices and so on if you're just thinking in terms of the undergrad procedure of how to evaluate a t test. Okay, so then let's start of where we are. So with the GLM, of course. So the major thing that we introduced is that under the GLM, the data is distributed according to this little expression here. So do you remember what that means? So can you give me some interpretation or say something about that? Anyone? Maybe interrupting your You're good. It's fine.
Someone moved the course an hour earlier.
Yeah, that's true. So what does that mean? What I've just written there? Yeah, it's you. This is
it's normally distributed with expectation parameter x beta.
What is that?
Atoms that really
Yeah, but what's the x beta? You know what the x beta is? Or no?
If I looked it up, it would be perfectly clear to me again.
So who remembers what x beta is?
X is the design matrix.
Yeah. And in terms of experiments, the beta encodes the effect size, as we will see later. Yeah, and what is interesting about this sigma square IN? Or why is there anything that you associate with the sigma square IN? Or is it just a sigma square and an IN?
The variance are independent.
Yeah, so the error contributions are independently distributed and identically distributed. Sorry, not identically distributed. I confused myself because they, of course, have different means because of the x beta. Okay, so that's basically, that's the foundation of what we're looking at. And then we discussed this formula. I'm doing it different today. I'm not asking you about the formulas, but I'm asking you about the meaning of the formulas. That's what I thought would be a great pedagogical exercise for the start of the year. So what do you associate with this formula that I just wrote here? Please, in the back. Do you associate anything? So if you associate something, please raise your hand. So you associate something. What do you associate with it?
As the estimator for the value.
And what kind of estimator is that? Do you? Yeah. What does that mean? Do you remember that?
So I think we took the first derivative of the...
No, but more intuitively. That's how we computed it, but intuitively, what does maximum likelihood mean?
So maxima is the likelihood.
What is the likelihood? I'm just trying to see how much these kind of things have consolidated. So the likelihood is the probability of the data as a function of the parameter. And what can you do with this formula? Or what else do you associate with this formula? I mean, you can do many things with this formula. You can ignore it, for example. Okay, it's not that interesting maybe. So you can compute a point estimate. Given some observation of the data, you can compute a point estimate of the beta parameters. And because these are your effect size of interest, that's something. Okay, so then what we also looked at was this formula. So who associates something with that?
That's the chi-square distribution of the... well, it's the variance parameter and it should be distributed according to the chi-square.
Yeah, so it's the variance parameter estimate or estimator. Yeah, we will see its distribution in a second, and it's associated with chi-square. That's definitely true. Can you associate something with, for example, the numerator?
Yeah, you call that the prediction error, so it's the It's the square actually of, I mean, it's the data minus the estimate, right? The y, the data y. So it's the difference and then times itself.
Yeah, so it's basically after computing the beta parameter estimate, you get a prediction for the data that you observed, which is given by the design matrix times the beta parameter estimator, and then the difference is what you can call, if you want, and you like this cog neuroscience nomenclature, you can call it a prediction error, and then, as you said, it's squared. And then it needs to be divided by this n minus p to get it into the right units. Yeah, but then you already said something about the distributions of these estimates, and I'm just writing up the first distribution that we looked at. So we saw this distribution. What do you associate with that? Who associates something with that?
Well, it's the same again for the beta parameter. It's the way it's distributed. It's the normal distribution.
And what does that mean in experimental context? So if you now have observed some data, do you then have a distribution of your estimate, or what does it mean?
Oh, it's the thing that you also said, it's not the reality, but on model.
Yeah, exactly. Yeah, so it's actually not reality. That's right. So it's, oops, there's the semicolon on the wrong point. Yeah, so it's basically if you or what you observe is a single realization from your model here. So from this, you observe a single realization, and hence you get a single point estimate for your parameters. But if you think that you would sample again and again under identical experimental circumstances, so basically with the same design matrix, the same true but unknown parameters, then you could observe this distribution. That's the logic of classical inference. Yeah, very good. And then you already said that the sigma square estimate is associated with the chi-square distribution, and that's true. It's actually the normalized version of the sigma square estimate, so divided by the true but unknown value of sigma square and multiplied by n minus p, which is distributed according to a chi-square distribution. So this thing is n minus p sigma square hat, and this chi-square distribution just has one parameter, namely the degrees of freedom, and the degrees of freedom parameter is given by n minus p, so a single number. So if you have 10 data points and 2 parameters or 2 effects that you want to estimate, then the degrees of freedom are 8. So the whole thing would be a little bit more beautiful if this thing was not normalized here, and then there would just be the distribution of this, but well, it's not about beauty, it's about things being correct, and this is how it looks. Okay, so this is basically all that we did until the week before Christmas. And it's quite a condensed representation, and it's of course important that you can associate the intuitions that we also discussed with these formulas. But in the end, it's just these 5 formulas that we really discussed. Okay, and based on this, we now proceed to go to t-statistics, where we will actually now combine certain aspects. So, everybody happy with the review? Questions about this that you think you would like to clarify now before we proceed? No. Good, but make sure that that you, on the one hand, know the formulas, on the other hand, can associate something with the formulas, but this all goes together. So I think it's not possible, as they try in psychology, sometimes to teach this stuff without the formulas, but then on the other hand, it's also completely meaningless to just have some formulas with no meaning. Good. Then let's, based on this, now talk about t-statistics. And yeah, so I'm doing it a little bit different than you might be used to. So we are not starting with the intuition, but start with the formal stuff and then get back to the intuition. So a t-statistic, based on what we've just seen, is defined as follows. It's defined as a function that depends on a contrast vector or contrast weight vector. Maybe I put it here, C in RP. So that's a vector, a p-dimensional vector. And one could, maybe let's have a look how it looks if we put the C, because it depends on the C, here as a subscript. It takes a p-dimensional vector and a scalar that is equal or larger than 0, and maps that, and that's important, to a single scalar, a real value. And what it actually takes is a beta estimate and a variance estimate. So these are this p-dimensional vector, that's the beta hat, and this value larger or equal than 0, that's this variance estimate. And maps this onto, of course, its value. And then, of course, the question is how this is defined. Maybe I put it down here. Now I forgot the C already. So the value that this t takes is defined as the contrast weight vector multiplied or transposed and then multiplied with the beta estimate vector and divided by the square root of sigma square hat the transpose of the weight vector xt x minus 1 and c. So that's essentially the new formula you can memorize. And you are waiting for a new formula to memorize all these days during Christmas. So that's the formula, and of course we have to now associate some meaning to it. One thing that you should note already, that this t value is a function of multiple things. One could actually, so I think I will remove the C again, because in principle one could also say that it's a function of the design matrix. We leave that implicit, that it's a function of a contrast vector, but it's in a given context for a given design matrix and a given contrast vector, it's a direct function of the beta estimate and the variance estimate. Yeah. So now this is the basic definition, and so this is also, and I'm not doing this for fun, of course, because this is exactly, like I said, what this kind of thing is what you see when you see a blob on the brain in fMRI papers. And it's computed almost exactly like that. There's one thing we'll have to add later on. But we first want to see what this means and associate some meaning with it. So the one thing that that helps is always to look at it in simple examples. So let's assume that we do IID sampling from a univariate Gaussian. Yeah. So and with n data points. So intuitively, we are in this case where you have this univariate Gaussian, which you could call a population, if you think of undergrad statistics, and you sample from it, so you obtain some n samples, and then you're trying to estimate what you used to call the population parameter. So, of course, we now have to frame this, as we already did, also in terms of the GLM, because, of course, this formula for the T statistic refers to the GLM. So, do you remember how we can cast this IID sampling from a univariate Gaussian with n data points as a GLM? So, do you remember what we have to define for that? No? But you were like, maybe? Anyone remembers we talked about that? No? It's all gone. Really? Or you're just unsure? If you're unsure, try it. If you have a little bit of an idea. But if it's completely blank, then don't say anything. If you have a suspicion. No? Yeah, there's a suspicion.
You mean understand the view?
Yeah, but how do we have to frame the GLM, or how do we have to define the GLM to implement univariate IID sampling with n data points from a univariate Gaussian? No, it's all gone. Well, there are some videos on YouTube, so you can always watch these videos and you will find that we discussed it at one point. Okay, so what we did in some of the old videos is that, of course, we want to cast it as a GLM, so we define it as a multivariate Gaussian. And of course, the important thing is always to, if you define or if you implement a specific special case in the GLM, something like simple linear regression, for example, multivariate regression or ANOVA, the question is always what are the X beta and essentially what are the X beta, especially if you're looking at spherical covariance matrices. Now, we want n data points, and we always have n data points, so our Y is our Y is n dimensional vector, and then the question is what is X for sampling a univariate Gaussian. So now, any suggestions? No? Rather less suggestions. So for univariate Gaussian, X is an n-dimensional vector, so there's only one effect size parameter, so we already know that beta is also just a scalar, and X is defined as a vector of n ones, so which is just a vector of n ones. So if you have 10 data points, there are 10 ones, one below the other. Sigma square is sigma square and in is in. And the interpretation that you can give to the beta, if you're thinking in terms of this product of n Gaussians, so if you like to see things in this way, where you usually call the expectation parameter mu, then this beta is, of course, your what you would call population parameter mu. Yeah. So this is what we looked at previously, and yes, we did. yeah, so that's the GLM representation of sampling a univariate Gaussian, because then IID, because then the expectation is always the same for each data point, because it's always multiplied by this 1. So this X beta becomes a vector of this single beta parameter, one below the other. And the sampling is, of course, done always with the same variance for each data point. So this is what this results in. Then we can, of course, for this, evaluate our beta parameter estimator. So that, like we've seen above, I have to do it without the definition, like we've seen above, is xt x minus 1 xt y. Now what we really have here is, of course, 1 to the power of minus 1, and here we have 1 y1 y2 yn. So what do we get? At least maybe let's start here to start again with matrix multiplication. So what is that if you evaluate it? That's the sum of the y's. So we get I1 to n of the yi. And what do you get here in the within the brackets? So if you multiply this vector of ones with itself, one of them transposed, n exactly, and then you have to do n to the power of minus 1, which is what? 1 over n. Yeah. So you get this, which is of course something familiar, namely the sample mean, which in undergrad statistics often is denoted by a bar over the y. Yeah. And then we can already look at our t-statistic. So in general, the t-statistic, or at least not quite, we have to define what our contrast vector is. So now we set the contrast vector to a single 1. And for this, now evaluate in this specific case, and I'm leaving out the dependency on beta hat and sigma square here. We look at our specific case. So what we actually have in the numerator is 1 times our beta hat, which is the which is the average of the data points, and in the denominator C is 1, so CT is also 1, and xt to the power of minus 1 we evaluated here, so that's 1 over n. So we get in the denominator the square root of sigma square divided by n. And this is then the same as the different ways to write it, and you always see different forms. So it can also be written like this, and divided by this, and then maybe even more popular is then to multiply it with the square root of n, which also actually is a little bit meaningful because it tells you something quite important. Somehow I can't write today. So we get, and I write it here again, we get t equals square root of n times the average of the data points divided by the empirical, divided by the standard deviation, yeah. And this formula that you should recognize from undergrad statistics. Who has seen this formula? Good. Then my inference is correct. So this is kind of the basic formula that you learn for the t-value in one sample t-test against the null hypothesis of the true but unknown value being 0. And it's quite informative, actually. So, and it's somehow, for some reason, also this formula gets often lost in people's heads. So there is, this is actually very important for understanding t-values. So one thing before we get to the importance is that this thing here, so the square root of the variance estimate, which is also known as the standard deviation, divided by the square root of n, this is also known as the standard error of the mean. Or SAN, and that's quite popular to plot because as error bars, because it's smaller than the standard deviation, and hence makes the plots look nicer. And yeah, but I think more informative is actually this representation of the t-statistics. So yeah, very important. First thing is that the t-statistic, in this case, is a ratio of, for the specific case, of the sample mean with the, in this case, the sample standard deviation. But it's also quite important that you now already try to generalize this from this univariate Gaussian thing to something more general, because here the sample mean is an estimate for the true but unknown value of this Gaussian mean, so this beta parameter. And you can always call this also the effect size, because what you're that's maybe a little bit easier to see when we talk about ANOVA, but it's implicit also in this case, because you can view that in the following, so the population might have an expectation of 0 for some trait, and or it might have an expectation of 10 for this trait, so that would be a much bigger effect for this trait. Yeah? So just in terms of intuition, you can try to get familiar of calling the beta parameters also effects, and it's easiest to see in terms of ANOVA, but you can also think about it in terms of simple linear regression, where we had the slope parameter. You can also consider this the kind of the effect that the value of x has on y, because the steeper it is, the stronger and y changes as a function of x. So it's always carries this notion of an effect without specifically defining what an effect now is, because in the end what it is a beta parameter, and so it's an effect size divided by a scaled version, a scaled version or scaled data variance. That's just maybe the best thing to say. So here, of course, this sigma head is an estimate for the sigma square parameter, the true but unknown, and is in the end some transformation of the true but unknown variance parameter. So what the t value really represents is a ratio between some size of effect, so some parameter size in terms of beta parameters, and the data variability. Yeah, so that's really important, because that's all it is. But that's also something, yeah. So if you have a high t value, that means that the effect size, whatever the effect size is in a specific scenario, is quite large as compared to the variability. So you get a single number representation of what you normally would need kind of two things for. So if you think about a bar plot and then looking at the error bars, you would here say, okay, the difference between these two bars is there, but there's also a lot of variability. Yeah? And you can put this into a single number, namely a relatively low t-value. Now, if you have the same thing with much less data variability, then you would say, okay, now the difference between these bars is still the same, but the data variability is much lower, so that looks more meaningful. So that's the first thing. And then the other thing that you also see from this T formula is the fallacy of classical inference, if you want, is that the T values increase with increasing sample size. Yeah? So the larger n, or more specifically, the larger the square root of n, but the square root just increases with n, the higher the T value. Yeah. So in the end, you can get things, so putting it informally, you can get things significant by increasing the sample size without actually increasing the ratio between the effect size and the variance estimate. And this, given all these discussions about power and so on, that's how it is. That's how classical inference works. You can have the same ratio of these and get the same ratio of effect size versus data variance. And if you increase your sample size, then this will at one point be meaningful, given the interpretation of high t values being something significant. Yeah. So questions about this. It's really important that you get this intuition. So I hope you got it. As a second example, if one is in a more general setting where beta is now a p-dimensional thing and not a scalar, then of course one can always compute a specific contrast by setting all the contrast weights to 0 except 1. So this should now be a vector of zeros with just one location with just one at location j. So we can also write that as so these are the elements of this C is 1 if I equals j and is 0 else. That's another way to write this, but it's just a vector of zeros with a 1 at a specific location. And then what the t-value does with its formulation is that you have this ct times beta, then, beta hat, then you single out a specific single parameter, right? So you have this, you multiply everything with a 0 in your estimator, but beta hat j, so you can single out a given parameter, and the same thing you do actually to the inverse of this, so you get a specific entry of this, we have already seen that as of the beta estimator covariance matrix. So that's oops, here we should fill in something. That's the case. Of course, it's a little bit, it's not that immediately and nicely to interpret as in the case of a univariate Gaussian sampling, because you somehow still have this thing here, and there you have to, it's actually not that easy to associate some meaning directly, or at least I haven't thought as deep as about this as I maybe should have. So, but what it shows is that you can, in terms of these doing effect size versus scaled data variance, you can always achieve that with contrast weights being 0 and 1 at a single location. And then, of course, what you will be very interested in is contrast weights of the form, let's say you have two beta parameters in a multiple linear regression design, contrast parameters of this form, because these kind of contrasts, they refer to what people then put in fMRI papers in terms of condition A larger than condition B. This might at this point not tell you much, because we haven't at all talked about how the GLM is adapted to the fMRI case. But if you have ever done an fMRI data analysis and you entered at one point contrast weights, you will have entered some interesting combinations of 1s and -1s usually. Who has done that? Has anyone done that? No? Nobody ever analyzed fMRI data? Who has analyzed fMRI data? But you didn't enter any contrast. You didn't do a GLM analysis then, I assume.
Well, you don't put in the -1s, right? You just click on this.
No, you have to. I mean, even if you're doing it in SPM, or not even if you're doing it in SPM, you have to specify contrast always. I mean, whether you do it with a script or you do it by hand, but you have to. Yeah. So you have to put in some combination of 1s and -1s, and these are exactly these C's that we are talking about. And then, of course, what you do with this is that you create differences. So, for example, if you have beta 1, and so if you have something like this, then with this contrast vector, you would create the difference at beta 1 minus beta 2. And then again, look for the size of this difference with respect to some measure of the variability. Yeah. Good. So I think I want to stop here. So this is this has nothing to do, and you should not confuse that. This has nothing to do with hypothesis testing, and this has nothing to do with p-values. This is just one statistic that you can compute based on some data. So by first computing the beta estimate and then computing the variance estimate and then putting these two together under specifying or with or simultaneously specifying a contrast vector, then you can compute this t statistic, and you get, importantly, you get a single number. So this is a single number, and with this single number, what it represents is a ratio of the effect size with the data variability, unfortunately scaled by the number of data points. Maybe to add that, then sometimes people say, yeah, but we want to see effect sizes. Or maybe they say it in a nicer way. Could you please show effect sizes? And then you might have heard something about Cohen's d, which is an effect size measure. And this is essentially a t-value just divided by square root of n. So to get rid of this effect of the sample size. But it's the same thing. It's just a transformation of the t-value. Yeah. So if people are somehow something a little bit annoying, not but they are like the t-values. We can't do t-values. We have to look at effect sizes. This is the same thing. It's just multiplied by or divided by a single number.
But there you say that the t-value assumes the effect size divided by the scaled data variance, but it's just scaled.
Okay. So, sorry. Yeah. This. Okay. So very good that you bring that up. This is my effect size, not Cohen's d effect size. The effect size that I mean here, is an important point, is not like a typical effect size thing that you know from statistics, but what I mean by this effect size is just the value of a parameter. And then, of course, there's Cohen's d as a measure of effect size, and this would take my effect size and divide it by the variance. Yeah. So, yeah, maybe put this into quotation marks so that you don't confuse it with effect size measures. But the thing is, what is an effect size? So that you can just have different measures of effect sizes. And what I'm using here as a measure of effect size is the raw estimated beta value. And of course, Cohen defined effect size as the ratio between the raw estimated beta parameter and the estimated variance. But I think because the important thing is that the t value is also a measure of effect size, but then again multiplied by the square root of n. Yeah. So this is intuition. This is why this is intuition. This is what's going on. Yeah. Other questions?
Can you say again what the y dash?
That's just the average. What's this?
Can you maybe explain the C again?
The C, that's just the contrast weight vector, and it allows you to essentially it gives you a very versatile means to look at different beta parameters, because so what is unknown in the GLM are the beta parameters. Yeah, so there are true but unknown effects of whatever you put into the design matrix. This is why I think a lot of people have problems thinking about beta parameters in this abstract manner, because the interpretation of the beta parameter really depends on the design matrix, and we've seen essentially 2 or 3 design matrices so far, one being the univariate Gaussian case, where it's just the expectation of some population. We've seen many times the simple linear regression, where the beta parameters get the interpretation of a slope and a offset, and multiple linear regression we've seen a little bit, where it's basically the different regressors. Now the C allows you to select specific parts of these beta parameters. For example, if you're only interested in the offset and not the slope in simple linear regression, then you could define contrast weight vector 1 and 0, so that in your t value you only look at the one for the offset, if that's what you're interested in. You can also view this C differently. So the beta parameter estimates, they're usually p-dimensional vector, right? So they are usually a multivariate thing. The C, so these contrast weights, they allow you, by means of this dot product, to project that onto a scalar. Yeah? So the t distribution is a univariate distribution, and if you want to use your t statistic with the t distribution, then you need a univariate representation of your beta parameters. So the C is always the interpretation then of a specific contrast vector depends on the interpretation of the specific beta parameters, and is something actually to think about, because this is, at least from my experience, specifically in fMRI data analysis, you have no idea usually. So somebody tells you have to use here the contrast 1, 1, minus 1, minus 1. But in the beginning, you have no idea why you use that. But then you associate with that, okay, that's this condition larger than this condition or something. But really to understand and also become efficient and self-efficient in defining contrast, you have to always, for a specific GLM, think about what do my beta parameters mean, and what does it mean if I now choose a certain set of contrast weights. How does this dot product turn out? That's the story about the C.
So can you maybe explain, in your example you said the C to 1, so what do you in this case?
Why? Or
What does it mean?
It doesn't mean anything. It just means that we don't. We could also set it to 2, but then we would have 2 on in the denominator and the numerator, and that would cancel out. It's more a kind of a dummy thing. It doesn't mean anything. It just leaves because the beta head estimate here turns out to be the average. It just leaves the average here. Yeah. It just works. You can also view it like this. It just works in this case to come to this formula. If you set the C to 1, then the thing works. Well, other questions? Good, then let's have a break and continue at maybe 10 past 10.